Section 16 of the Science History of the Universe, Volume 4. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science History of the Universe, Volume 4, edited by Francis Rolt-Wheeler. Chemistry. Chapter 12. The Development of Organic Chemistry. Lavoisier showed that organic substances were composed principally of carbon, hydrogen, and oxygen, together with nitrogen and sometimes sulfur and phosphorus. He had observed that an element was capable of forming more than one oxide, and from this he concluded that organic radicals deported themselves similarly. He consequently regarded sugar as the neutral oxide d'un radical hydrocarboneux, and oxalic acid as its higher oxide. He even hazarded the conjecture that the fatty oils, which he considered to be hydrocarbons, might actually constitute organic radicals in the free state, and might, by oxidation, be converted into neutral oxides and vegetable acids. Among Lavoisier's other investigations in organic chemistry, his research on the process of vinous fermentation is worthy of mention. He expressed the results in the form of the equation 3 ounces 7 gross of water plus 2 pounds 8 ounces sugar produce, on fermentation, 1 pound 7 ounce 5 gross 18 grains of alcohol plus 1 pound of carbonic acid. In this equation, says he, there is only sugar whose constitutional parts are unknown to me. I know the composition of water, of alcohol, and of carbonic acid, and nothing is easier than to substitute these values in the equation established and then deduce the constituent parts of sugar. However, Lavoisier did not regard organic chemistry as a separate division of the science. He classed all acids together, and like Lemery in 1675, subdivided them into mineral, vegetable, and animal acids. With a few exceptions, the immediate followers of Lavoisier followed the same plan, and the division of chemistry into inorganic and organic chemistry was not generally adopted until it became clear that several compounds occur both in the vegetable and animal kingdom, and therefore that no difference existed between vegetable and animal chemistry. In this connection, the work of M. E. Chevreul, 1786 to 1889, should be emphasized, as it was his investigations which demonstrated that many of the fats and acids and other substances occurring in both kingdoms were identical. However, for some time subsequently, considerable doubt prevailed as to the boundary of inorganic and organic chemistry. One reason for this was that inorganic substances, as well as some which had to be considered as organic, gave on analysis numbers which demonstrated that their composition was in accordance with the laws of constant and multiple proportions. As Berzelius stated in 1811, the majority of organic substances, however, appeared not to obey these laws, and consequently he undertook to decide this question by the analysis of a large number of them. After years of labor and after improving the appliances and methods of organic analysis, he finally obtained results which proved that although most organic compounds possessed a much more complicated composition than the mineral compounds, yet they obeyed the laws of constant and multiple proportions. He adopted the views of Lavoisier and said, after we got a clearer insight into the difference existing between the products of organic and inorganic nature, and the different manner in which their ultimate components are united with each other, we find this difference consists really in the fact that in inorganic nature all oxidized bodies contain a simple radical, while all organic substances are oxides of compound radicals. The radicals of vegetable substances consist generally of carbon and hydrogen, and those of animal substances of carbon, hydrogen, and nitrogen. In his ideas as to these radicals, he was especially influenced by the research of Gay-Lussac upon cyanogen, in which he showed that this radical played the role of an element. Attempts were multiplied to discover the various organic substances having complex groupings of atoms which performed as elements. Thus Gay-Lussac regarded alcohol as ethylene and water. Dobereiner considered oxalic acid as carbonic acid and carbon monoxide. As Berzelius pointed out, this was opposed to the electrochemical theory, and there was danger of confusion and error. The search for the proximate constituents in organic substances induced a rapid development of the science. leading especially to many efforts at definitely determining the chemical constitution of these bodies. One of the most important of the discoveries in the third decade was that of isomerism. This was viewed as an error by chemists at first, so little prepared were they to believe that bodies similarly composed could be chemically and physically different. It was in the year 1823 that Liebig announced that his analysis of silver fulminate yielded the same results as Wöhler had found in the preceding year for his silver cyanate. He was confident that his figures were correct, and believed that Wöhler must have made a mistake. A careful repetition of the analyses showed him that both were correct, and so it was proved that two bodies, totally unlike, could and did have the same composition. Gay-Lussac saw that the only explanation of this lay in the different mode in which the elements were combined. In 1826, Berzelius reported on Liebig's fulminate of silver as follows. This substance has been made the subject of a new joint investigation by Gay-Lussac and Liebig, and the result is of the utmost interest. Fulminate of silver dried at 100 degrees loses all its water, and in 3 experiments they found between 16.87 and 17.38% cyanogen, the mean being 17.16%. The silver oxide was separated by hydrochloric acid and was found to be 77.528% of the weight of the salt. These quantities add up to 94.688%. The deficiency is only 5.312%, a quantity absolutely equal to that of the oxygen in the silver oxide. Hence, the salt was composed of 77.528% of silver oxide and 22.472% of cyanic acid. But this result is identical with that obtained by Wöhler in his analysis of silver cyanate, in spite of which agreement between the analytical results, the two substances have not the same properties. The chief difference is that Wöhler's cyanate of silver, when heated by itself, does not explode, but only burns with moderate intensity. And further, that when decomposed by acids it is completely changed into carbonic acid and ammonia, while fulminic acid has explosive properties and gives ammonia and prussic acid when its salts are decomposed by oxyacids. These facts point unquestionably to a difference in composition. Jahresbericht, 1826. In 1825, Michael Faraday announced the results of his work on the hydrocarbons from oil gas, when he demonstrated the existence of butylene, an isomer of ethylene. In 1827, Berzelius commented on this discovery in part as follows. The two gases are of like constitution, but a given volume of the one contains twice as many simple atoms as does the other, and this produces a certain dissimilarity in physical and chemical character. Definite knowledge concerning this phenomenon would be of such significance in the doctrine of the composition of vegetable and animal bodies, and would have so important a bearing on organic chemistry, that it must not be accepted as demonstrated until its truth has been subjected to the most severe proof. It is not my intention to dispute the possibility or the actuality of such a fact, but I maintain that before accepting it with confidence, the relation observed by Faraday must be found in a number of other cases. In 1832 and 1833, Berzelius formally adopted the addition to the doctrine of chemical composition rendered necessary by these observations, and suggested his classical classification of the new phenomena, concluding as follows. But since it is requisite that we should be able to express our conceptions by definite and appropriately chosen terms, I have proposed to call substances of the same composition and of different properties isomeric, from the Greek isomeri, composed of equal parts. The general designation isomerism has since then been retained. Berzelius soon saw himself necessitated to define more strictly the meaning to be attached to this word, and therefore he distinguished between polymerism and metamerism as special cases of isomerism. The ideas of Berzelius with regard to the probable cause of isomerism in organic compounds are clearly shown in many of his statements. In his view, isomeric compounds are those in which the atoms of the elementary constituents have grouped themselves differently into compound radicals. The isomerism of compounds in itself presupposes that the positions of the atoms in them must be different. and it appears that he considered it possible to determine the mutual relations of the atoms in their compounds. At the period that is now reached, to quote Carl Schorlemmer, we find Berzelius laying stress again on a difference between organic and inorganic substances, first pointed out by Gmelin, 1817, and according to which the latter, but not the former, could be prepared artificially. Berzelius was of opinion that within the sphere of living nature the elements obeyed laws totally different from those ruling in inanimate nature. It was then commonly supposed that the compounds found in plants and animals were produced by the action of a so-called vital force, and that although they might be changed into other compounds, none of them could be prepared artificially from their elements. Thus grape sugar, a compound widely distributed in the vegetable kingdom, by fermentation yielded alcohol, which could be converted into ether, acetic acid, and many other compounds, and all of these were considered to be organic, as none of them could be prepared synthetically. It was Friedrich Wöhler's synthesis of urea which finally removed this obstacle to the growth of organic chemistry. In 1828, Wöhler made the discovery that cyanate of ammonia, which was regarded as an inorganic compound, could be converted into urea, a substance hitherto known only as a product of animal metabolism. This was the first synthesis of an organic compound, and is generally referred to as marking the beginning of scientific organic chemistry. Yet it remained an isolated fact for a long time, and failed to shake the belief in a vital force, a belief which was maintained during the lapse of many years. In 1830 and 1831, Liebig perfected and simplified the operations for the ultimate analysis of organic compounds, and this to such a degree that his processes have not required any essential alterations to fit them to modern requirements. These perfected methods enabled Liebig to carry out his famous researches in Gießen, work which renders a brief biographical mention of this master fitting. Justus Liebig was born at Darmstadt on May 12, 1803. The fact of his father being a dealer in dyestuffs brought him early into contact with laboratory problems. At 15 years, he was sent to a neighboring town to learn the business of apothecary. But pharmacy was not chemistry, as Liebig was beginning to understand it, so he entered the University of Bonn. Here was certainly change, much ingenious contemplation, but no chemistry. He traveled to Erlangen, where he heard lectures, read books, and at 19 obtained a degree. Then his chance came. His ability being made known to the Grand Duke of Hesse-Darmstadt, he was provided with the means of studying in Paris. There worked closely giants Gay-Lussac, Thenard, Chevreul, Vauquelin, and Dulong. Nor was it long before Liebig was received into the laboratory of Gay-Lussac. Liebig had meanwhile won the appreciation of Humboldt. His was a personality that inspired immediate and warm friendships. Of slender form was he, a friendly earnestness in his regular features, great brown eyes with shady eyebrows, which attracted one instantly. It was Humboldt who, in 1824, brought him as extraordinary professor of chemistry to Gießen. 2 years later, he was elected to the ordinary professorship, which office he held for the next 26 years. The dull little town of Gießen became famous. The fires of Liebig's laboratory acted as a beacon light, attracting chastened spirits from the four quarters of the civilized world. For it was not long before the master had roused the Darmstadt government to build a laboratory where all might come and seek and find. And the movement spread. Liebig, through his pupils, tinctured the world. There were other governments than that of Darmstadt, and soon there were other public laboratories than that of Gießen. In 1845, Liebig was created baron. In 1852, he accepted a call of the Bavarian government to the Munich professorship of chemistry. Warmly appreciated by the Bavarian court, entering into the social and philosophical life of the university town, courted by all the scientific circles of Europe, yet continually fighting weakening health, Liebig passed the remainder of his life in Munich. He died in 1873. Liebig devoted his full powers of mind to organic chemistry, but did not neglect inorganic chemistry, as his work on the compounds of silicic acid, alumina, and antimony clearly shows. His work in physiological and agricultural chemistry rendered him a general benefactor of mankind, and to quote A.W. von Hofmann, if we sum up in our minds all that Liebig did for the good of mankind, in industries, in agriculture, and in the laws of health, we may confidently assert that no other man of learning, in his course through the world, has ever left a more valuable legacy behind him. Writing in 1810, Gay-Lussac and Thénard gave, as a reason for the slow progress of animal and vegetable chemistry, the inadequacy of the methods of organic analysis. In their Recherches physico-chimiques, which appeared in 1811, they gave an exhaustive description of a new method of organic analysis, the results of analyses of sugar, starch, gum arabic, milk, sugar, wood, and mucic, oxalic, tartaric, and acetic acids, as well as of oils, resins, and waxes, and the following generalizations made from the results of their work. 1. A vegetable substance is always acid when it contains more oxygen than will form water with the hydrogen. 2. It will be always resinous, oily, or alcoholic when it contains less oxygen than suffices the hydrogen. 3. The body will be neither acid nor resinous, but analogous to sugar or ligneous fiber when the oxygen and hydrogen are present in just the proportions to form water. This classification was, of course, of little service, but it was suggestive, and although no proper classification was possible at this time, the interpretation of Gay-Lussac and Thénard gave a stimulus to the study of the constituents of organic compounds. Berzelius explained in 1819 that his electrochemical theory could not be extended to organic chemistry because under the influence of the vital force, the elements there possessed entirely different electrochemical properties. In decay, putrefaction, fermentation, etc., he observes phenomena which he regards as demonstrating the tendency of the elements to return to their normal condition. He did not, at that time, as yet consider it possible to regard all organic substances as binary groups. Dualism was, indeed, extended as far as possible. The oxygen compounds were looked upon as oxides of compound radicals, which, however, do not exist free, but are wholly hypothetical, a mode of regarding the matter which was especially applicable to the acids. In 1838, Liebig defined a compound radical enunciating three characteristics and making use of cyanogen as an instance. We term cyanogen a radical because 1. It is the unchanging constituent of a series of compounds. 2. Because it is capable of replacement in these by simple substances. And 3. Because in those cases where it is combined with one element, this latter can be exchanged for its equivalent of another element. At least two of the conditions here adduced had to be fulfilled in order that an atomic complex might be stamped as a radical. The existence of these conditions, moreover, could only be established by the most minute investigation of the chemical behavior of organic bodies. That is to say, the nature of the radicals assumed in the latter could only be arrived at from the study of their reaction and decomposition products. This radical theory aroused considerable interest, and chemists of eminence were attracted to the task of investigating the constituents of compounds related to one another. Thus the research of Bunsen upon cacodyl compounds, which formed one of the strongest supports of the theory, may be mentioned. Robert Wilhelm Bunsen, 1811 to 1899, enriched every branch of chemistry by his valuable researches. He created the gas analysis methods of today. With Kirchhoff, he developed spectrum analysis into one of the great branches of today, and in his investigations in analytical and inorganic chemistry and in geochemistry, he showed himself a pioneer in the science. Bunsen's researches on the cacodyl compounds resulted in the proof that the so-called alkersin, the product of the distillation of acetate of potash with arsenious acid, contained the oxide of an arsenurated radical, arsenic 2, carbon 4, hydrogen 12. Hydrogen equals 1, carbon equals 12, arsenic equals 75. This radical remaining unchanged in a long series of reactions of that oxide, and being even itself capable of isolation. This compound element, containing arsenic, an unusual constituent of organic bodies, was thus shown to be a true radical. Inasmuch as the radical was supposed to be constituted of atoms held together by stronger forces than those which united the group to other atoms, it attained a real significance in the minds of chemists, and as the dualistic theory and the theory of compound radicals became more solidly entrenched in chemistry, they rendered the atomic theory, on which of course they were founded, an essentiality, and even after dualism was discredited, the only changes were in the ideas as to the nature of the ultimate particles, or atoms. About this time, however, facts became known which could not be brought into accord with the radical theory, and as a result doubts were expressed as to the theory of dualism. But it was the discovery of the principle of substitution which actually caused this theory to succumb, and paved the way for the so-termed unitary theory. The conception of equivalence might have led to that of replacement or substitution, since the quantities of two acids were equivalent when they saturated the same quantity of a base. The acid in a neutral salt could thus be replaced by its equivalent without the neutrality being interfered with. The word replacement received further justification after Mitscherlich had studied the phenomena of isomorphism. It could then be said that certain elements in a crystal might be replaced by others without alteration of the crystalline form. Such substitutions possessed the peculiarity, however, that they were not connected with any proportions by weight, and it may thus appear all the more remarkable that they should render important assistance in the determination of atomic weights. The hypothesis underlying the phenomena of isomorphism was that one atom could only be replaced by one other, that is to say, that the numbers of the atoms in isomorphous compounds must be identical. Since chemically similar substances had alone been compared, an extension of the prevailing views, based on the phenomena of isomorphism, would have been quite possible, but this class of phenomena had never led to any attack upon the system. In the bleaching of wax by means of chlorine, Gay-Lussac had observed that for every volume of hydrogen eliminated, an equal volume of chlorine was taken up. He had also found the same thing in the action of chlorine on hydrocyanic acid. In the course of their investigation of the benzoyl compounds previously referred to, Wöhler and Liebig, when acting with chlorine upon bitter almond oil, had discovered benzoyl chloride, and they expressly remarked that this substance is produced from the bitter almond oil by 2 atoms of chlorine taking the place of 2 of hydrogen. In the year 1834, Dumas, apropos of an investigation on the mutual action between chlorine and oil of turpentine, but more especially of his work upon the production of chloral from alcohol, condensed into 2 empirical rules the facts with regard to substitution, for which he proposed the designation metalepsy, that is, exchange, metalepsis. These were not intended to comprise a theory of substitution, as his first utterances on the subject show, but only to give expression to the facts. They were as follows. When a compound containing hydrogen is exposed to the dehydrogenizing action of chlorine, bromine, or iodine, it takes up an equal volume of chlorine, bromine, etc. for each atom of hydrogen that it loses. If the compound contains water, it loses the hydrogen of this without replacement. The second of these rules was deduced from the transformation of alcohol into chloral, and was thus intended to explain the mode of formation of the latter and at the same time to support Dumas' view of the constitution of alcohol, the latter being regarded by him as a compound of ethylene and water. By means of various examples, Dumas further endeavored to prove the general validity of the laws which he advanced. In establishing the correct composition of the Dutch oil, he pointed out that the chloride of carbon obtained from it by means of chlorine and examined by Faraday supplied a new argument in favor of the accuracy of his views. He also found similar support in the action of chlorine on hydrocyanic acid, on bitter almond oil, etc. However, he was unsatisfied with this and extended his statement to one of greater significance, regarding oxidations as cases of substitution, as, for instance, the conversion of alcohol into acetic acid. While Dumas limited himself at this time, 1835, to condensing the known facts into the above laws, Auguste Laurent, 1807 to 1853, a pupil of Dumas, went further, and considered the nature of the compounds resulting from substitution, and made a comparison of them with the original ones. He was thereby induced to enunciate the proposition that the structure and chemical nature of organic compounds are not materially changed by the entrance of chlorine and the separation of hydrogen. This law is the core of the substitution theory proper, of which Laurent was the propounder. Laurent endeavored to give expression to the observed facts and to the hypotheses based upon them in the so-called Nucleus Theory. This theory is of importance in the science, although it never obtained any general recognition in it, because chemists have adopted, if in another form, many of the ideas embraced by it, and also because it was adopted by Gmelin as the basis of the organic portion of his excellent handbook. On this account, the chief points of Laurent's doctrines will be stated. According to Laurent, all organic substances contain certain nuclei, which he calls either fundamental, radicaux fondamentaux, or derived. The former are compounds of carbon with hydrogen, in which the mutual proportion of the number of the atoms is a simple one, 1 to 2, 3, 4, etc., 2 to 3, etc. For any definite proportion, several nuclei exist which are polymeric among themselves. Besides, these fundamental radicals are so chosen that the hydrogen and carbon atoms contained in them occur in pairs. The derived nuclei, radicaux dérivés, were produced from the original nuclei, either through the substitution of hydrogen by other elements or by the addition of other atoms. This theory manifestly sprang from the old radical theory, but with an important change, namely, the radical here is not an unchanging group of atoms, but it is a combination which can be changed through the substitution of equivalents. It is but a step in the evolution of the modern theory as seen in the benzene nucleus. The Nucleus Theory was regarded as unscientific by Liebig, and Berzelius opposed it, but the latter was moved before long by Malaguti's investigation of the simple and compound ethers, in which he demonstrated that the chlorine atoms again played the part just as the hydrogen atoms they had displaced, and as Armitage observes in his History of Chemistry, he saw that here was the thin edge of a most potent wedge, which, unless immediately removed, might break down the whole fabric of that chemical theory he had spent so much on building. Before Laurent, in conjunction with Gerhardt, had again brought forward his ideas in a more perfect form, Dumas entered the lists to do battle against the radical theory, and with this, against the dualistic idea in general. His beautiful discovery of chloroacetic acid afforded him the immediate occasion for this, and he now gave in his adhesion to Laurent's opinions, which formerly he would have nothing to do with. By the action of chlorine in sunlight upon acetic acid, Dumas had obtained a crystalline substance whose composition could be expressed by the formula carbon 4, chlorine 6, hydrogen 2, oxygen 4, and which could, therefore, be regarded as acetic acid, carbon 4, hydrogen 8, oxygen 4, in which 6 atoms or volumes of hydrogen were replaced by 6 atoms of chlorine. The interesting and important part of this reaction lay in the properties of the new compound, which Dumas called chloroacetic acid. This acid had the same saturating capacity as acetic acid, so that Dumas was able to assert that by the entrance of chlorine in place of the hydrogen, the chief character of the compound was not altered, or, as he expresses himself, that in organic chemistry there are certain types which persist even when an equal volume of chlorine, bromine, or iodine is introduced into them in place of the hydrogen which they contain. He was thus led to the same view which had already been taken up by Laurent, but his theory of types, 1839, was hardly a mere application of the views of Laurent. The principal propositions of this theory were as follows. 1. The elements of a compound body can, in many cases, be replaced by equivalents of other elements or of compound bodies which play the part of simple ones. 2. If such a substitution occurs equivalent for equivalent, the compound in which the replacement has taken place retains its chemical type, and the element or group which has been taken up plays in it the same part as the element which has gone out. The term chemical type failed to satisfy Dumas, however, and he permitted it to merge into that of mechanical type, which included all compounds which might be supposed to be formed from one another by substitution, even though they differed in properties. Berzelius could not accept these views, and when Dumas characterized his electrochemical theory as erroneous, an embittered discussion ensued which lasted for years. The proposition of Dumas that every chemical compound forms a complete whole and cannot therefore consist of two parts, that its chemical character is dependent primarily upon the arrangement and number of the atoms, and in a lesser degree upon their chemical nature, proclaimed a decided Unitarism, and was therefore violently opposed by Berzelius. Berzelius sought to get over the difficulties which the substitution of hydrogen by chlorine and other elements involved by arguing that compounds formed in this manner must have a constitution different from that of the original ones. But here he entered upon dangerous ground, and was thereby led, prudent investigator as he was, into the most utter contradictions of the principles which he had formerly held to be inviolable. Facts now increased which went to demonstrate the correctness of the theory of substitution, and in 1842 Melsens found that by the action of potassium amalgam on a water solution of trichloroacetic acid, its chlorine was completely replaced by hydrogen, acetic acid being reproduced. This was a discovery of the greatest import, as it showed inverse substitution was possible, yet it did not shake Berzelius's faith. He merely decided to look upon acetic acid in the same way as its chlorine derivative, that is, as a copulated oxalic acid with the copula methyl carbon 2H3, formulating the two compounds thus: carbon 2 hydrogen 3 plus carbon 2 oxygen 3 dot hydrogen oxygen acetic acid, carbon 2 chlorine 3 plus carbon 2 oxygen 3 dot hydrogen oxygen chloroacetic acid. This was practically giving up the fight, as by it he acknowledged that the parling or copula could undergo substitution, and that its exact nature did not have a predominating influence in determining the nature of the compound into which it entered. Yet Berzelius remained an opponent of the theory of types until his death in 1848, and his adherents experienced great difficulty in reconstructing radicals anew from his copulae after his death. In 1845, A. W. Hoffman discovered the substituted anilines, and observed that it appeared without doubt that chlorine or bromine could assume the role of hydrogen in organic compounds, taking their electronegative character with them into the new compounds. Liebig commented on Hoffman's report as follows: "The author appears to have definitely proved that the chemical nature of a compound does not in any way depend upon the nature of the elements contained in it, as is assumed by the electrochemical theory, but entirely on their arrangement." Liebig now turned to the unitary theory and opposed Berzelius's attempted explanations. Other prominent chemists, too, became his opponents, and yet, in spite of the slight regard in which the radical theory was held in many quarters, it soon became evident that, for the investigation of chemical constitution, the assumption of radicals, which had been displaced by the theory of types, was indispensable. In the fifth decade, a fusion of the radical theory with the doctrine of types occurred on the unitary side, and as a result of the work of Auguste Laurent and Charles Gerhardt, 1816 to 1856, the older theory of types was transformed into the new theory. In 1839, Gerhardt published his views on the process which occurs when an element is replaced by a group of atoms. In his opinion, it was not a substitution, but a union of two residues to a unitary whole, and not an articulated binary compound. He termed these groups of atoms les restes or les restants, and later developed his theory of residues, according to which a residue could have the composition of a compound radical, but was not present as such in a compound. His conception of radicals soon replaced the older views, and its introduction into the theory of types induced a fusion of both theories. The first advance in this direction was made in 1849, when C. A. Wurtz, 1817 to 1884, discovered the compound ammonias. Hoffman found another method of preparing the bases discovered by Wurtz, and the typical view of these bases was first arrived at by means of his investigations. He showed that in the amine bases, as well as in aniline, the two hydrogen atoms of the amide could be replaced by alcohol radicals. A. W. Williamson, 1824 to 1904, then demonstrated that in a similar manner the alcohols and their ethers could be referred to the type water. He also pointed out that acetic acid must have a constitution similar to that of alcohol, and proposed to call the radical carbon 2 hydrogen 3 oxygen obtained from ethyl by oxygen substitution, othel. Gerhardt, employing a reaction similar to that by which Williamson had prepared the ethers, discovered the anhydrous acids, and chemists began to attempt to find among the more simple inorganic compounds other types for organic compounds, thereby giving rise to Gerhardt's theory of types. According to this theory, the organic compounds of known constitution can be classified under 4 types, namely hydrogen, hydrochloric acid, water, and ammonia. For example, the hydrocarbons, aldehydes, and the acetones or ketones were classed in the first type, the halides, chlorides, bromides, iodides, and fluorides in the second, the alcohols, ethers, monobasic acids, and sulfides and hydrosulfides in the third, and the amines were placed in the fourth type. The general arrangement and the comprehensive character of Gerhardt's system leave nothing to be desired. Even although views have been considerably changed and cleared up since that time, and although one is compelled, from the modern standpoint, to look upon the types as insufficient, still, Gerhardt's services to chemistry can never be questioned. Unfortunately, he did not live to witness the reception which was extended by many chemists to the views laid down by him in the 4th volume of his Lehrbuch der organischen Chemie. The type theory was particularly extended by the assumption of mixed types, which was intended to render clear the relations of many organic compounds to 2 or more types. This was particularly applied by August Kekule. It was also in the 5th decade that Hermann Kolbe, 1818 to 1884, revived the much ridiculed copulae. He and Sir Edward Frankland, 1825 to 1899, were followers of Berzelius, and held similar views to Gerhardt. But as they did not accept at that time either the new atomic weights or the existence of radicals containing oxygen, they made use of other formulae. Kolbe united the conclusions deduced from his researches with the declining theory of Berzelius. He induced the latter with new life by casting aside whatever of it was dead and replacing this by vigorous principles. From his own and other investigations he came to the conclusion that the unalterability of radicals, as taught by Berzelius, could no longer be maintained, since the facts of substitution had to be taken into account. He did indeed adopt Berzelius's hypothesis of copulae, but attached another meaning to these, since he allowed that they exercised a not inconsiderable influence upon the compounds with which they were copulated. He endeavored to make this theory have a deeper bearing upon the constitution of organic compounds, and as a result of the influence of several important researches, his ideas regarding copulae and conjugated compounds were altered several times. His theoretical views, and with them the revived radical theory, reached their completed form in a contribution published in 1859. The principal result of Kolbe's speculations is given as follows. Organic compounds are all derivatives of inorganic, or result from the latter, in some cases directly, by wonderfully simple substitution processes. This idea runs through the 1859 contribution and is illustrated by numerous examples from the wide field of organic chemistry. End of Chapter 12. Section 16.
Section 17 of The Science History of the Universe, Volume 4. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in June 2017. The Science History of the Universe, Volume 4, edited by Francis Rolt-Wheeler. Chemistry. Chapter 13. Valence, the constitution of organic compounds, and the development of stereochemistry. In the preceding chapter, mention has been made of the influence exerted by Frankland on the views developed by Kolbe respecting the constitution of organic compounds. It was Frankland who, in his now classical paper, A New Series of Organic Compounds Containing Metals, demonstrated that the pairing of the radicals with the elements was to be explained on the ground of some characteristic property of the atoms, and thus he expelled the useless part of the radical theory. 1852. Frankland observed that, quote, "When the formulae of inorganic chemical compounds are considered, even a superficial observer is struck with the general symmetry of their constitution. The compounds of nitrogen, phosphorus, antimony, and arsenic especially exhibit the tendency of these elements to form compounds containing 3 or 5 equivalents of other elements, and it is in these proportions that their affinities are best satisfied. Thus, in the ternal group we have NO3, NH3, Ni3, NS3, PO3, pH3, PCl3, SbO3, SbH3, SbCl3, ASO3, ASH3, ASCl3, etc., and in the 5-atom group NO5, NH4O, NH4I, PO5, PH4I, etc. Without offering any hypothesis regarding the cause of this symmetrical grouping of atoms, it is sufficiently evident, from the examples just given, that such a tendency or law prevails, and that, no matter what the character of the uniting atoms may be, the combining power of the attracting element, if I may be allowed the term, is always satisfied by the same number of these atoms." End quote. He then proceeded to represent the organometallic compounds obtained by formulae which brought out the analogy with the inorganic types from which they were thought to have been derived. From his work on the organometallic compounds, Frankland developed the doctrine of the valence of the elements, the germ of which may be recognized in much that has gone before, particularly in the law of multiple proportions, which stated that the elements show different yet definite stages in their combinations. The so-called doctrine of the polybasic acids contributed materially to the development of ideas upon the subject of the saturation capacity of the atoms. Gay-Lussac, Gmelin, and others inclined to the assumption that the atoms of the various metallic oxides contained one atom of oxygen united to one atom of metal, and that these oxides combined with one atom of acid to form neutral salts. Berzelius also, after 1628, considered that this combining proportion was the rule. However, by Thomas Graham's famous investigation of the phosphoric acids, 1833, it was shown that a view so simple as this, according to which almost every acid was looked upon as monobasic, was untenable. Graham proved that in the ortho-, pyro-, and metaphosphoric acids, for each atom of phosphorus pentoxide, there were 3, 2, and 1 atoms of basic water, these latter being replaced by equivalent amounts of metallic oxides. The saturation capacities of these acids were in this way shown to be dependent upon the amounts of basic water which entered into their constitution. Liebig extended this to many other acids and distinguished between mono-, di-, and tribasic acids, and the property was referred to as the basicity of the atoms, a term which, with the ideas inherent in it, clung for some time to the theory of valence. In 1857, for example, the terms basicity, valency, and atomicity were used as synonymous, and as the measure of the number of hydrogen atoms that could be replaced or held in combination. The idea of basicity was soon extended to the compound organic radicals. In 1855, C. A. Wurtz (1870–1884), a pupil of Liebig and Dumas, showed that glycerin C3H8O3 may be regarded as the hydrate of the radical C3H5. 4 years previous, A. W. Williamson (1824–1904) had expressed the view that a large number of compounds may be referred to the type of water, the monobasic acids to one molecule, and the polybasic acids, which are of greater molecular complexity, to a condensed water type. He wrote C2H3O HO equals acetic acid. SO2H2O2 equals sulfuric acid. Wurtz now showed that the composition of glycerin could be represented by the formula C3H5 H3O3, which was similar to the formula by which, in accordance with the ideas of Williamson, ordinary phosphoric acid PO3' H3O3 was represented. Gerhardt, in his Traité de chimie organique, stated that, quote, "In order to compare the radicals among themselves, I propose to refer them all to the radical of hydrogen, and consequently I name them monatomic, diatomic, triatomic, according to the quantity of hydrogen which they are capable of replacing in the type H2O, that is, according to whether they are equivalent to 1, 2, or 3 atoms of hydrogen, so for instance in alcohol and in ether, O C2H5 OH, C2H5 O C2H5. C2H5, the radical ethyl, is monatomic because it replaces H, one atom of hydrogen, in the type water." End quote. The terms monatomic and polyatomic had been employed much earlier, but in a different sense. Thus, in 1827, Berzelius called fluorine, chlorine, etc. polyatomic, because several atoms of these halogens unite with a single atom of another element. In 1833, Gaudin de Saintes used the same terms to express the number of atoms in a molecule, in which sense they were used by Gmelin, Clausius, and Odling. Williamson attached the idea of capacity for saturation or atomicity of the radical to the number of hydrogen atoms capable of substitution, and the notion of atomicity was soon extended to the known compound radicals and played an important part in the theory of types, etc., which obtained in organic chemistry. Frankland's speculations concerning the substitution value of radicals compared with that of elementary atoms were of great importance, yet they did not meet with immediate approval. By 1858, however, the Valence theory had made rapid progress. In this year, Auguste Kekulé first deduced the valence of carbon from its simplest compounds, declaring it to be tetravalent. This had already been recognized by Kolbe and Frankland, if not expressly stated by them. But Kekulé rendered further and much greater service by inquiring into the manner in which 2 or more of these tetravalent carbons were united with one another. The doctrine of atomic chains, open and closed, sprang from this, and the domination of the structural idea in chemistry became complete. In the same year, and independently of Kekulé, M.S. Couper arrived at conclusions almost identical with those of Kekulé. Both Kekulé and Couper expressed with absolute definiteness the axiom that the atomicity of the elements was to be made use of for arriving at the constitution of chemical compounds. The idea of the term atomicity had without any doubt been introduced by Frankland 6 years previous to this. The further development of the above axiom and its utilization in the theory of the linking of atoms was carried out mainly by Kekulé, and in the succeeding years also by Butlerow and Erlenmeyer. While the radical and type theories were attempts at securing an idea of the structure of chemical compounds, it was the Valence theory which rendered it possible to furnish a lucid answer to the question as to the composition of such bodies, and, especially after the year 1870, the determination of the constitution of complex molecules became the higher aim of chemistry. Some rudiments of systematic classification had before this been introduced into organic chemistry, and these classificatory beginnings were of great assistance in the erection of structural chemistry. In 1836, Laurent, when he brought forward his Nucleus series, arranged organic compounds in series, and it was in 1841 that Gerhardt entered on a research to discover some general law which might suggest an all-sufficing system of classification, and the following year he was ready with his ladder of combustion, with its highest rung cerebral matter, its lowest carbonic acid, water, and ammonia, to enfold the whole science of organic chemistry. He soon found, however, that this arrangement, according to mere complexity of composition, was no sufficient classification, so he betook himself to another line of inquiry. A note of triumph seems to ring through the following lines from the preface to his Précis de chimique organique, published in 1844. Quote, "I have succeeded in establishing homologous series. These have indicated to me the means of classifying organic substances in natural families, and of disposing them on a kind of combustion ladder." End quote. As a matter of fact, it was only the word homology that Gerhardt could claim as his own. 2 years earlier, J. Scheele had shown that a very simple relation existed between the alcohols then known, that their radicals might all be represented by the general expression Nr plus H, R suggesting the group C2H2, C = 6. Moreover, in the same year Dumas had demonstrated the existence of a similar relation between the several members of the fatty acids known to him. Yet Gerhardt generalized from this fact of homology, and proved the possibility of predicting the existence of terms unknown in his series. Many systems of classification were suggested during the 6th decade, the classification by series as that of Scheele and Dumas, that of series depending upon formulae, series depending upon chemical behavior, and many other systems. The lack of agreement among chemists, however, as to the formulae belonging to the different compounds, as to the relative weights of the molecules, the atomic weights, and even the number of atoms, prevented a general acceptance of any of the classifications proposed until Kekule established the fact of the tetravalence of the carbon atom, showed the difference between saturated and unsaturated compounds, and deduced his chain formulae. About 1860, Frankland's views regarding a saturation capacity peculiar to the elements were accepted either dilettantly or expressly by most chemists, but it was considered that this saturation capacity, under certain circumstances, might be a varying one. In 1856, Gerhardt had stated that nitrogen was sometimes triatomic and sometimes pentatomic. This view was also held by Frankland, Wurtz, Williamson, and Couper, and the latter three considered that the valence was also variable in the cases of many other elements. Kolbe thought that it must be assumed that a constant valency was characteristic of a few elements, and a varying one characteristic of many more, since he perceived in it another expression for the law of multiple proportions, and nothing was known concerning the cause of valence. As early as 1854, Kolbe had concluded that each element possessed a maximum saturation capacity, but that lower stages of saturation might exist along with this, and toward the beginning of the 60s, several chemists who took an active part in developing the structure theory expressed the same opinion in a more definite manner. Erlenmeyer, in particular, maintained in various papers, and afterward in his Lehrbuch der organischen Chemie, that each element possesses a maximum valency, or that each is furnished with a definite number of Affinivalenten, or affinity points, Affinitätspunkten, only part of these, however, being in many cases combined with the affinity points of other elements. Kekule's theory of the constant valence of the elements could not withstand the critical examinations to which it was subjected, however, and in the course of the last 40 years the majority of chemists have adopted the view that the atoms of most of the elements possess a varying saturation capacity, varying according to the conditions. Although the structure theory was unable to accomplish the extreme expectations which aimed at a knowledge of the special arrangement of the atoms, it possessed nonetheless great practical value. The development of organic chemistry since the middle of the 6th decade shows in fact that, through the aid of the structural hypothesis, the discovery of new modes of formation and decomposition of compounds, the recognition of the relations existing between various classes of bodies, and, especially, the interpretation of the constitution of numerous organic substances became possible. Kekulé's theory of the aromatic compounds forms the most striking proof of this. In 1865 to 1866, taking the quadrivalence of carbon as his principle, Kekulé called attention to the fact that in the fatty compounds the carbon atoms are linked together by one valence of each. In the case of benzene, the next simplest assumption was made, in accordance with which the carbon atoms are linked together by 1 and 2 valencies alternately, so as to form a closed chain or ring. Of the 24 affinities of the 6 carbon atoms, 18 are employed in linking carbon to carbon. Thus, 6/2 times 4 plus 6/2 times 2 equals 18. 6 valencies then remain which are satisfied by the 6 hydrogen atoms of the benzene. Hence, according to Kekulé, benzene may be represented by means of a regular hexagon whose sides are composed of single and of double lines alternately, the CH groups occupying the corners, thus. Kekulé and his pupils, together with many other chemists who had busied themselves with the derivatives of benzene after this view had been published, now directed their efforts to comparing all the known and rapidly increasing observations bearing upon this class of bodies with the deductions drawn from the above formula, and therewith to proving by actual experiment the admissibility of the assumptions on which the formula was based. The result was that Kekulé's anticipations were realized and his hypothesis substantiated. In 1866, Kekulé had stated that, quote, "What is wanted is that the largest possible number of substitution products of benzene should be prepared by the most diverse methods, that they should be most carefully compared with regard to isomerism, that the modifications so found should be counted." End quote. And in the 1867 edition of his textbook, he called attention to a number of cases of isomerism which at that time had received no explanation. Among these we find that of ethylene chloride with ethylidene chloride, of acetal with diethyl glycol, for maleic and fumaric, for mucic and saccharic acids. The last effort of his philosophy had only found him the two formula C4H2 double prime O2H2 O2 and C6H8 double prime O6H2 O2 respectively. Kekulé instanced, too, those bodies which only differed in their effect on polarized light, the tartaric, the malic, and camphoric acids, and the amyl alcohols. It was owing to these cases of isomerism that structural formulae could not be assigned. In some cases a greater number of isomeric bodies were known than could possibly be accounted for by any arrangement of the atoms in formulae upon a plane surface, retaining, of course, the accepted views as to valence, etc., and since these isomers differed principally in certain physical properties, they were at first termed physical isomers. The study of these resulted in the consideration of the arrangement of atoms in space, the chemistry of space or stereochemistry, in which branch of the science an extended view of atomic grouping was essayed. Modern stereochemistry was anticipated by Emanuel Swedenborg in 1721, when he made an attempt to explain the phenomena of chemistry and physics on geometrical principles in his Prodromus Principorium Rerum Naturalium sive Novorum Tentaminum Chemiam et Physicam Experimentalem Geometricae Explicandi, and similar beginnings were made by Johann Barcussen 10 years earlier. In 1864, Carius, who first used the term physical isomerism, explained it as follows. Quote, I have tentatively expressed a view as to the cause of what I call physical isomerism. Substances which exhibit this property yield, under the same or nearly the same conditions, products which are either identical or physically isomeric. According to our present views, I think it improbable that such substances should have their atoms differently arranged, that is, that they should be metameric. But it is quite conceivable that in the formation of physical isomers, differences of condition may cause the production of substances with the same arrangement of the atoms within the molecule, but with a different aggregation of these molecules, and that thereon depends the difference in their properties. Thus, we must consider as certainly only physically isomeric a large number of the substances distinguished by the difference of their action on polarized light, such as the two modifications of amyl alcohol, the tartaric acids, the malic acids, etc. This explanation was inadequate, and in 1873 Johannes Wislensius 1835 to 1902, who succeeded Kolbe as professor of chemistry at Leipzig in 1885, suggested the substitution of the term geometrical isomerism for physical isomerism. He had been engaged in an investigation of the various modifications of lactic acid, and had found that the ethylene lactic acid, or hydrocrylic acid, prepared by Beilstein by treating beta-iodopropionic acid with silver oxide, possessed properties different from those of the ethylene lactic acid obtained from ethylene cyanhydrin. This difference was so marked that he thought it might be explained by assigning the two acids different structural formulae. The first was optically inactive, while the second, paralactic acid, was dextrorotary. This one point of difference appeared hardly sufficient to make it necessary to assign to paralactic acid a structural formula other than that of fermentation lactic acid. It seemed much more likely that here, at any rate, were cases of what Carius had called physical, but what Wislicenus now proposed to call geometrical isomerism. He said, quote, My conclusion for the present is to declare paralactic acid and the fermentation lactic acid as most probably only geometrically isomeric. Their great similarity, even identity in all chemical properties, the ease of transformation on heating of the first into the second, and their differences, particularly in optical behavior, may all alike be explained on this basis. Concerning the special how of this explanation, I am engaged in experimental investigations. The next year J.A. van 't Hoff furnished an answer to this. However, before giving his exposition, mention must be made of Louis Pasteur's (1822 to 1895) pioneer work in this field. Pasteur studied the various tartrates crystallographically, and showed that there are 4 isomeric tartaric acids, i.e., racemic acid, inactive tartaric acid, and right and left rotating tartaric acids. He showed, moreover, that the 2 latter acids crystallize in similar, but in oppositely built up, enantiomorph forms, that they both rotate a ray of polarized light through equal angles, but in opposite senses, and that when mixed in equal quantities they yield optically inactive racemic acid. Further, he succeeded in decomposing racemic acid again into the 2 optically active tartaric acids by 3 different methods. Pasteur established the correlation of molecular dissymmetry and rotary power in these investigations, and it remained to discover under which conditions the dissymmetry could obtain in 2 molecules structurally identical. This was undertaken in 1874 by J.A. Van't Hoff in Holland and J.A. Lebel in France, who in papers published that year offered an explanation practically the same for cases of isomerism which could not be included under the theories of the time. Van't Hoff states that in general Lebel's original paper and his were in accord, but that while Pasteur's researches formed Lebel's starting point, he took for his own Kekullé's laws of the tetravalence of carbon, to which he added the hypothesis that the 4 valencies are directed toward the corners of the tetrahedron in the center of which is the carbon atom. To quote from Freund's Study of Chemical Composition, quote, Van't Hoff introduced no fundamental change in or addition to the original valency hypothesis. A 2-dimensional representation of molecular structure could not at any time have been considered as really true to the actual occurrence, but it was legitimate to use it, because of its greater simplicity, as long as it proved adequate to the purpose. And with this recognition and restriction, we continue to use plain structural formulae in the majority of cases. End quote. Van't Hoff, following up the suggestion that may be found implied in Pasteur's paper, and that was explicitly stated by Wislicenius, introduces into the science the consideration of the arrangement of atoms in space. Quote, Stereochemistry, from stereos, solid, in the restricted sense of the word, comprises chemical phenomena which demand a consideration of the grouping of atoms in space. End quote. Carbon compounds only were considered at first, but the scope of the phenomena dealt with has been extended and now includes compounds of trivalent and pentavalent nitrogen, of tin, and of sulfur. Van't Hoff's theory of the asymmetric carbon atom, however, met with difficulties on its enunciation. To quote from F. P. Armitage's History of Chemistry, quote, when Van't Hoff enunciated his theory of the asymmetric carbon atom, he was able to say, with much show of truth, that all optically active substances did contain certainly one such atom. Soon, however, were heard dissentient voices. What of propyl alcohol? Asked one, and of styrolene? Demanded another. The propyl alcohol owes its activity to traces of amyl alcohol, answered Henninger. The styrolene is impure, said Van't Hoff, and their evidence was irrefutable. But Van't Hoff could not, in 1874, maintain that the presence of one asymmetric carbon atom necessarily implied optical activity, for secondary amyl alcohol and its derivatives, also propylene alcohol, were certainly inactive, yet all contained an asymmetric carbon atom. The problem, said the stereochemists, was somewhat similar to that of the relation between tartaric and racemic acid, so happily solved years before by Pasteur. His methods were recalled, and Lebel soon showed that these inactive bodies were in reality mixtures of 2 optically opposite isomers, and, others helping, that indeed every substance with but one asymmetric carbon atom was equally capable of mesotomism. The 4 varieties of tartaric acid had offered no difficulty. With 2 asymmetric carbon atoms similarly habited, there was necessarily neutralization or duplication of optical activity. But where 2 or more carbon atoms occurred, asymmetric by union with different radicals, as in the sugars and their derivatives, many more cases of physical isomerism suggested themselves and have since been verified. Without doubt, the asymmetric carbon atom has made a triumphant progress, winning for Lebel the Jecker Prize of 1881, for Van't Hoff a dominant voice in the scientific councils of the world. It will rank with the phlogiston of Stahl, the oxygen of Lavoisier, the atom of Dalton, and the dualism of Berzelius. End quote. Among the most noted workers in the field of stereochemistry have been A. von Baeyer, Wallach, Victor Meyer, Rieke, Bischoff, Werner, Hantzsch, Auwers, and Overton. Even now the subject is in its infancy, and stereochemical theories are as yet insufficiently advanced to present a clear view of the question of geometrical isomerism. Yet, as Ladenburg has said, quote, "It is beyond doubt that the founding and development of stereochemistry, a name which originated with Victor Meyer, is the most important thing that was accomplished in organic chemistry during the last 2 decades of the 19th century. Stereochemistry possesses a significance for this period similar to that which the foundation and introduction of the theory of aromatic compounds possessed for the 20 years preceding." End quote. End of section 17.
Section 18 of the Science, History of the Universe, Volume 4. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science, History of the Universe, Volume 4, edited by Francis Rolt-Wheeler. Chemistry, Chapter 14, Modern Inorganic Chemistry. Progress in inorganic chemistry during the modern period. A rapid growth in inorganic chemistry ensued after the introduction of the new chemistry by Lavoisier. A mass of information concerning the nature of the elements and their compounds was accumulated, and many new bodies were discovered. However, even now, after the accurate study of the chemical behavior of mineral substances by many careful investigators, we are still far from a definite knowledge of the nature of all the elements and their compounds, and new bodies are from time to time added to the extensive series already known. In the case of the elements, for example, Lavoisier in his Traité de Chimie mentioned 26, while 81 are at the present time accepted. An endeavor to sketch the important advances in inorganic chemistry since the time of Davy and Gay-Lussac will be made in this chapter. Cadmium was discovered by Strohmeyer in 1817 and about the same time by Hermann. It was named by Strohmeyer cadmia fornicum, or furnace zinc, because it was found in the zinc furnace, cadmia being the original name for zinc. In the same year, lithium was discovered by Arfvedson in petalite and spodumene. The metal was first obtained by Bunsen and Matthiessen in 1855. The name is Greek and means stony, and the metal was so called because it was then supposed to be found only in rocks, and not in the plant and animal bodies. Silicon was first isolated in 1810 by Berzelius by fusing together iron, carbon, and quartz, and Wohler showed that it exists in the crystalline form as well as in the amorphous state. In 1827, Wohler isolated aluminum by the action of potassium upon its chloride, and 18 years later St. Clair Deville prepared the metal on a large scale by using sodium, while Bunsen effected its preparation by electrolytic means. Aluminum is now prepared in quantity by the electrolytic decomposition of the oxide alumina dissolved in cryolite. Beryllium or glucinum was also obtained by Wohler, who effected its isolation in 1828 by the action of potassium upon the chloride. Bromine was isolated by Ballard in 1826 from the mother liquor of sea salt, and was further investigated 3 years later by Lowig, along with iodine, which was discovered by Courtois in 1811 in the ashes of sea plants, and chlorine. It constituted the group of halogen elements of Berzelius, since fluorine was then unknown. The latter was first isolated in 1886 by Moissault by the electrolysis of hydrogen fluoride in the presence of potassium fluoride. Tellurium, which had been discovered by Müller von Reichenstein in 1782, was thoroughly investigated by Berzelius, who discovered an element chemically analogous to it, selenium, in 1817. The isolation of the metals comprising the cerium and yttrium groups has presented numerous difficulties. Although the discovery of yttria, impure it is true, from admixture with other earths, was accomplished by Gadolin in 1794, and investigators have busied themselves with the question, the chemistry of the cerium metals is not even yet completely elucidated and may possibly remain unsolved for considerable time to come. After Klaproth and Berzelius had independently prepared cerium sesquioxide from cerite, and the latter had identified this as the oxide of a metal, Mosander discovered two new oxides in crude yttria, the metals of which, lanthanum 1834 and didymium 1841, he isolated. 2 years later, 1843, he added to these two others, erbium and terbium, whose existence and nature is not yet, however, definitely settled, in spite of the admirable work which has been done on the subject. This has given us a better knowledge of yttrium, while yttria, which was formerly held to be a homogeneous substance, has proved itself a mixture of the oxides of various metals, of which, however, only one or two has yet been isolated. For example, the discovery of scandium by Nilsson and Cleve in 1879, and ytterbium by Marignac. The most recent additions to the knowledge of chemistry of this group of elements and their compounds have been made by Welsbach, Drossbach, Kruse, Winkler, Crookes, Bronner, Baskerville, Urbain, and others. Welsbach separated didymium into prasseo and neodymium. An analytical method has been elaborated for the separation of the various constituents of cerium, ytterbium, and thorium earths, which has been of help in the manufacture of mantles for incandescent light burners. Quite recently, Urbain has separated ytterbium into two other elements, neoytterbium and lutetium. In spectrum analysis, chemistry now possesses an exceedingly valuable instrument for investigating rare metals and earths, and its use in the last 5 decades has been extensive. Spectrum analysis has grown out of some apparently insignificant and disconnected observations made by Marggraf, Scheele, Herschel, and others upon the light emitted by flames colored by certain salts. The spectra of such flames were investigated by various scientists, among whom Talbot, Miller, Alter, and Swan deserve first mention, but it was only after Kirchhoff in 1860 proved the definite statement that every glowing vapor emits rays of the same degree of refrangibility that it absorbs, that spectrum analysis became developed by Bunsen and himself into one of the great branches of our science. Its importance for analytical chemistry, especially in the discovery of new elements, is almost beyond mention, and it opened up a new era in chemistry. Roscoe once said, "The spectroscope, next to the balance, is the most useful and important instrument which the chemist possesses." Crookes has remarked, "If I name the spectroscope as the most important scientific invention of the latter half of this century, I shall not fear to be accused of exaggeration." The very importance of the subject prevents an entrance into any long discussion of it here. It has come to form a distinct branch of chemical science. In the hands of men like Bunsen and Crookes, it has explored the recesses of the rocks for minute traces of hidden treasures, while with it workers like Miller, Huggins, and Lockyer have fathomed the abysses of space and determined the constitution of the stars. Among the elements discovered by the use of the spectroscope were rubidium and caesium in lepidolite, and in the Durkheim mineral water by Bunsen and Kirchhoff; indium by Reich and Richter in 1863 as a constituent of Freiberg zinc blende; gallium in 1875 by Lecoq de Bois-Braudron; and thallium by Crookes in 1861. The chemical nature of the last mentioned metal was established by Lamy in the same year. The knowledge of the metals discovered in the preceding era was greatly enlarged by investigations conducted during this period. The analogues of nitrogen, phosphorus, arsenic, antimony, and bismuth were carefully examined, and the atomic weight which Berzelius determined for phosphorus was confirmed by Dumas, while his atomic weight for arsenic was corroborated by Pellouz and Dumas. The metals of the alkaline earths, barium, strontium, calcium, and magnesium, which were isolated by Davy, were investigated by Berzelius, Marignac, and Dumas, who determined their atomic weights. Recently, Winkler found that magnesium is an excellent reducing agent for metallic oxides. Cobalt and nickel have been the subject of researches of an important nature, mainly because of the remarkable compounds they form, for example, nickel tetracarbonyl and the ammonio-cobalic compounds. Nickel is now extensively used in metallurgy, especially in the production of nickel steel. The rarer metals have, of course, received considerable attention. Uranium, which was discovered by Klaproth in 1798, was investigated further by Pelago, Roscoe, and lately by Zimmermann. Molybdenum and tungsten, isolated respectively by Helm and Del Hurriar, have become better known, and the acids and the complicated salts of these have been studied by Scribler, Marignac, Friedheim, and Gibbs. Uranium, and particularly tungsten and molybdenum, are now employed extensively as steel hardening materials. Uranium compounds are also used in dyeing and ceramics. Titanium, zirconium, and thorium have now become, in the form of various compounds, particularly the oxide, of practical importance. Thorium was discovered by Berzelius in 1828. Its oxide, thoria, is applied in the manufacture of Welsbach gas mantles, which consists essentially of a web of 99% thoria and 1% cerium oxide. Titanium is employed for the manufacture of special alloys, and zirconium, as zirconia, is made use of both in gas and electric illumination. Germanium, an element which resembles these in some respects, was discovered by Winkler in 1886 in a Freiberg silver ore. The element vanadium, which was discovered by Del Rio in 1801, was isolated by Roscoe in 1867. He also investigated its compounds carefully, determining its different stages of combination with oxygen and chlorine. This metal, which is widely distributed, is utilized in the production of sheet and tool steel and armor plates. Tantalum, a related metal, which along with columbium or niobium was examined exhaustively by Blomstrand and Marignac, is used in alloys to make small springs and anvils, and in the metallic form to make special incandescent electric light filaments. The metals of the platinum group, platinum, palladium, Woolston in 1803, rhodium, Woolston in 1804, iridium, Tennant in 1803, osmium, Tennant in 1803, and ruthenium, Claus in 1844, have been given careful consideration by chemists. Platinum is used extensively in making chemical apparatus, especially crucibles and stills, and osmium and iridium have recently come into use as filaments for incandescent lamps. About 15 years ago, the number of the chemical elements was enlarged by two gases of great theoretical interest, argon and helium. As early as 1785, Cavendish had noticed that a residue of about 0.6% remained when the nitrogen and oxygen were removed from air, and in 1894 Rayleigh discovered that nitrogen from the atmosphere was 0.5% heavier than nitrogen prepared chemically. Rayleigh and Ramsay then prepared large quantities of this atmospheric residue and found it to be a gas different from nitrogen. They called it argon, from the Greek argos, for lazy. Helium was discovered by Ramsay in 1895 in the mineral cleveite. It had already been found to exist in the chromosphere of the sun by Janssen in 1868, and his observations were confirmed by Franklin and Lockyer. Helium, primarily obtained by heating cleveite with sulfuric acid, and since found in small quantity, often together with argon, found in the minerals uraninite, malacone, etc., as well as in the gases from some mineral water springs, is like argon, inert and indifferent. Up to now, in spite of persistent effort, no compound of either argon or helium has been prepared. And further, although many diffusion experiments with both gases have been carried out, with the object of seeing whether they were really elementary, the densities of both have remained unaltered. For example, It has been found impossible to subdivide them by diffusion into two or more components. From the ratio of the specific heats at constant volume and constant pressure, it follows that the molecule and atom are identical in both argon and helium. For example, that the gases are monatomic. And this applies also to the more recently discovered gases of the air, krypton, neon, and xenon. These were separated from liquid air in 1898 by Ramsay and Travers. The atomic weights of these gases and the proportions in which they are present in the air are as follows. Helium, atomic weight 4, 1 part by volume in air, 2,450 volumes. Neon, atomic weight 20, 1 part by volume in air, 808 volumes. Argon, atomic weight 39.9, 1 part by volume in air, 105 volumes. Krypton, atomic weight 81.8, 1 part by volume in air, 746,000 volumes. Xenon, atomic weight 128, 1 part by volume in air, 3,846,000 volumes. Since the interest attached to these gases has been recently augmented by the discovery of Ramsay and Soddy that radium emanation eventually changes, at least in part, into helium, and since Ramsay has shown that when the radium emanation decays in the presence of water, neon is produced, and that argon results when the decay takes place in the presence of water containing a copper salt in solution, the radioactive elements may be conveniently referred to here. Henri Becquerel found in 1896 that compounds of uranium spontaneously and continuously emit some radiation, which, among other properties, has that of making air a conductor of electricity. This effect, the quantity of which can be determined with great accuracy, was used by Madame Sklodowska-Curie to measure the amount of radiation produced by various compounds of uranium and of thorium, which latter had been found by Schmidt to emit the same kind of radiation. She subsequently tested a large number of rocks and minerals, and found that certain minerals which contain uranium and thorium, for example, pitchblende, oxide of uranium, chalcolite, double phosphate of copper and uranium, possess radioactivity much greater than that theoretically due to the amount of uranium present. Madame Curie therefore inferred that it appeared probable that if pitchblende, chalcolite, etc., possess so great a degree of activity, these substances contain a small quantity of a strongly radioactive body differing from uranium and thorium and the simple bodies actually known. I thought that if this were indeed the case, I might hope to extract this substance from the ore by the ordinary methods of chemical analysis. The investigation was consequently pursued, and with the assistance of her husband Pierre Curie and Gustave Beaumont, Madame Curie commenced the laborious treatment of the residue remaining after the extraction of the uranium from pitchblende, a large quantity of which had been placed at her disposal by the Austrian government, and finally separated the salts of radium in 1898. While endeavoring to isolate radium, Madame Curie discovered polonium, and other investigators, de Biernet, Gazelle, Markwald, and Hoffmann, have given the names of actinium, emanium, radiotellurium, and radio-lead to similar substances, the two last being possible products of the spontaneous change in radium. Among those who have worked with success upon the problem of radioactivity, Elster and Gettel, Rutherford, Soddy, and Ramsay may be mentioned here. Radium maintains a temperature 1 or more degrees above that of the atmosphere, injures the eyes, and disorganizes the flesh when kept long in contact with it. Its peculiar properties have been explained in various ways. The most plausible suggestion is that atoms of high atomic weight slowly disintegrate into ultimate corpuscles or particles, and that this decomposition is attendant with the development of great energy. The successive disintegration of the radium atom, as exemplified by the disintegration of products, is shown in the following table, which represents, according to Ernst Rutherford, the complete radium series as at present known. Radium, radiation emitted, alpha particles, period 2000 years. Range of alpha particles in air at normal pressure, 3.5 centimeters. Radium emanation, radiation emitted alpha particles, period, 38 days. Range of alpha particles in air at normal pressure, 4.3 centimeters. Radium A, radiation emitted alpha particles, period, 3 minutes. Range of alpha particles in air at normal pressure, 4.8 centimeters. Radium B, radiation emitted beta particles, period, 26 minutes. Radium C, radiation emitted alpha and beta particles, gamma rays, period, 19 minutes. Range of alpha particles in air at normal pressure, 7.06 centimeters. Radium D, radiation emitted unknown, period, 40 years. Radium E, radiation emitted unknown, period, 6 days. Radium F, radiation emitted beta particles, period, 4.5 days. Radium G, radiation emitted alpha particles, period, 140 days. Range of alpha particles in air at normal pressure, 3.86 centimeters. It appears that uranium is the source of radium, and Boltwood has recently announced the immediate parent of radium, ionium. Radium represents barium chemically, and according to Madame Curie and Thorpe, it has an atomic weight of 226.5. Several observers have demonstrated that it possesses a characteristic spectrum, and consequently, notwithstanding its disintegration and peculiar conduct, radium is regarded as a chemical element. Owing to an affidation among chemists to recognize a body as a chemical element when, under proper conditions, it possesses a definite atomic weight and exhibits a spectrum containing characteristic and novel lines. In 1823, Mitscherlich discovered the existence of sulfur in two different crystalline varieties, rhombic and oblique, and a third variety, a plastic form, was also known. Frankenheim learned that by heating and cooling, these varieties could, at definite temperatures, be converted into one another, and in describing these phenomena, the term isomerism was employed, to which, however, Berzelius published an objection in 1841. To quote from his Jahresbericht for that year: "I feel compelled to call attention to the fact that the word isomerism, which is applied to different substances composed of an equal number of atoms of the same elements, is not compatible with the view as to the cause of the different properties exhibited by the various modifications of sulfur, carbon, silicon, etc. While the term still lends itself to the expression of the relation between ethyl formate and methylacetate, it is no longer suitable in the case of simple substances which assume different properties, and it might be desirable to substitute for a better chosen term, for example, allotropy or allotropic modifications. In accordance with these views, there can be more than one cause for that which we call isomerism, namely, 1. Allotropy, in which case the difference between the sulfides of iron is due to the fact that they contain different modifications of sulfur. 2. Differences in the relative position of the atoms in the compound, of which the two kinds of ether, ethyl formate and methylacetate, are so striking a proof. 3. A combination of 1 and 2. Since then the term allotropy has been in constant use, and numerous allotropic phenomena have been observed, particularly among the non-metals. The allotropism of carbon was the first observed example, 1773, and its modifications exhibit marked points of difference. For instance, comparing diamond and graphite. Carbon, diamond, crystallographic system, cubic, optical properties, colorless, transparent, high refractive index, mu equals 2.417. Chemical and physical properties: non-conductor of heat and electricity, not attacked by oxidizing agents, ignition temperature 760 degrees to 875 degrees, specific gravity 3.52, hardness 10. Carbon, graphite, crystallographic system, hexagonal or oblique? Optical properties, opaque. Chemical and physical properties: Good conductor of heat and electricity, oxidized to graphitic acid, ignition temperature 575 degrees and above. Specific gravity 2.25, hardness 1. When amorphous carbon, coal, peat, lampblack, etc., and diamond are heated, they pass into the graphitic variety, and graphite is now produced in large amounts by heating carbon to a high temperature, 4,000 degrees Celsius, by an alternating electric current. Henri Moissan, 1852 to 1907, an eminent French chemist, succeeded in preparing synthetic diamonds by dissolving pure sugar charcoal in molten pure iron and suddenly cooling the mass by plunging it into water, and 3 English chemists, Sir F. A. Abel, W. H. Noble, and Sir William Crookes, obtained diamonds by exploding some of the high explosives in steel bombs, the liquid carbon produced crystallizing as it cooled. However, no diamonds have thus far been produced of commercial size or amount. The most peculiar, as well as noteworthy, example of allotropism is afforded by the conversion of oxygen into ozone. Ozone was first noticed by Van Marum in 1785 in electrified air. In 1840, C. F. Schonbein called attention again to this substance, discovering its oxidizing action, and showed that it was produced in the electrolysis of water and in the slow combustion of phosphorus and sulfur. He gave it the name ozone, which means a smell. The investigations of Marillac, de la Rive, Becquerel, Tate, Fremy, Andrews, and Brodie have proved it to be modified oxygen. Its density was determined by Sauret in 1860. The latter, and before him Andrews, proved that the ozone molecule contains 3 atoms of oxygen, while a molecule of the latter is made up of 2 atoms. Ozone is now used in the sterilization of water. Among other allotropic modifications, those of selenium and phosphorus are of interest. Berzelius investigated the allotropes of selenium, and those of phosphorus were studied by Berzelius, Schroeder, Hittorf, and Schenck. Schroeder discovered the red variety in 1845, and Hittorf found that it could be transformed into a metallic modification. Several additional allotropes of sulfur have been discovered in late years, and the fact that many metals can exist in allotropic forms has been clearly demonstrated, for example, colloidal gold, silver, platinum, and mercury. The list of the compounds of the elements was greatly extended from the time of Lavoisier, particularly with the discovery of new acids and the growing knowledge of the different basicity of the various acids. It is important to mention some of the discoveries of moment. In 1818, one of the most interesting of inorganic compounds was discovered by Thenard. He proved that water is not the sole oxide of hydrogen, but that another, peroxide of hydrogen, but which he termed oxygenated water, may be prepared. This compound plays a prominent role in many processes of nature and is now prepared in quantities by treating barium dioxide with sulfuric acid for disinfecting and bleaching purposes. The list of the halogen acids was completed prior to 1820. Gay-Lussac and Ballard studied hydriodic and hydrobromic acids. The former, Davy and Faraday, investigated hydrochloric acid, while Thenard, Gay-Lussac, and Berzelius contributed greatly to an intimate knowledge of hydrofluoric acid. In 1869, Gore and Nicholas continued the investigation of anhydrous hydrofluoric acid, and the latter lost his life through its action. Gore and Fremy established its composition, but, as before mentioned, the element fluorine was not isolated until 1886. The oxygen compounds of chlorine, iodine, and bromine have been given much attention since the commencement of the 19th century. The work of Gay-Lussac on chloric acid, Ballard on hypochlorous acid, Milan on chlorous acid, and Davy and Stadion on chlorine peroxide was exceedingly valuable, and led to researches which firmly established the composition of these bodies. The oxygen compounds of iodine received careful attention in the hands of Davy and Magnus, and the latter discovered iodic acid, the principal compound of that halogen. Following Gay-Lussac's discovery of hyposulphurous acid in 1813 and dithionic acid in 1819, little attention was given to the compounds of sulfur and oxygen until the fourth decade, when the thioacids, which contain more sulfur and are more closely related to sulfuric acid, were recognized. More recently, the early known oxides of sulfur, sulfur dioxide and sulfur trioxide, have received several additions in sulfur sesquioxide, sulfur tetroxide, and sulfur heptoxide. Sulfuric acid, the most important of all chemicals, is used in enormous quantities in the industries, and its manufacture has been immensely developed. Over 2 million tons were used in the United States in 1908. The very poisonous compounds of hydrogen with phosphorus, arsenic, and antimony, phosphine, arsine, and stibine, were given considerable attention during the first and second decades of the modern period. Phosphine, or hydrogen phosphide, discovered in 1783 by Gendebray, and its composition was studied by Davy. Rose continued its investigation at a later date. Arsine was prepared in a pure state by Soubrane. Galen fell a victim to its toxic action in 1815. Phosphorus and phosphoric acids were known to Lavoisier, but their constitution was not established until a much later period. It was upon the relations which Gay-Lussac, Stromeyer, and Graham found existing between the ortho, pyro, and metaphosphoric acids that Liebig founded his theory of polybasic acids, which marked such an important step forward in chemistry. The important compound, hydroxylamine, which may be regarded as ammonia in which a hydrogen atom has been replaced by hydroxyl, OH, was discovered by Lawson in 1865. It has led to a knowledge of many remarkable organic compounds. Similarly, the analogous compound, hydrazine, which was first prepared by Curtis in 1887, has entered into the preparation of a series of interesting compounds, for example, the hydrazones and hydrazides. It is an exceedingly powerful reducing agent. Of the simple carbon compounds, the greater number were discovered in the first decade. Carbon disulfide, which was accidentally discovered by Lampadius in 1796 while heating pyrites with coal, was accurately examined by Vauquelin in 1812. It is now prepared in an electric furnace by conducting sulfur vapor over heated carbon, and finds extensive use as a solvent. Carbonyl chloride, or phosphine gas, was discovered by Davy in 1811, and carbon oxysulfide by von Than quite recently. The compounds of carbon with certain metals, carbides, are now of great technical importance. In 1808, Davy discovered potassium carbide, the first described in chemical literature, and in 1862 Wohler prepared calcium carbide, now one of the most important on account of its use in the generation of acetylene and in the manufacture of calcium cyanamide, a new constituent of fertilizers. Calcium carbide has, since 1894, been prepared by fusing limestone and carbon together in an electric furnace. Before closing this brief resume of some of the advances made in the knowledge of chemical compounds, mention must be made of the metallic peroxides, hydrides, and nitrides. Sodium peroxide, which was discovered by Gay-Lussac, is now used extensively under the name oxone as a bleaching and oxidizing agent, and calcium peroxide, discovered by Gay-Lussac and Thenard, is used in dentistry. The discovery of the hydrides belongs to the present day. Among the most important of these is calcium hydride, or hydrolyte, which is used for generating hydrogen. The metallic nitrides, as magnesium, calcium, boron, and lithium nitrides, have only lately been investigated carefully, but may become of great importance. Numerous important chemical and physical facts were learned concerning the gaseous bodies, especially during the second, third, and seventh decades, and the experiments which were conducted with a view of liquefying gases are of the highest import, more particularly with regard to the production of liquid air and its application to researches at low temperatures. The experiments of Davy and Faraday, in which the gases were generated in curved, closed glass tubes and cooled to about -20° C in a freezing mixture, resulted in the liquefaction of all the common gases, with the exception of hydrogen, nitrogen, oxygen, methane, carbonic oxide, and nitric oxide. In 1834, Thurier liquefied carbon dioxide in considerable quantities and obtained the solid. He was the first to operate on a large scale, and subsequent investigators made use of many of his observations. Between the years 1844 and 1855, Naderer studied the relationship of pressure and volume over wide ranges of pressure, and in 1852 he exposed hydrogen to a pressure of 2,790 atmospheres, but was unable to effect its liquefaction. It was only in 1877 that Raoul Pictet and Louis Cailletet succeeded, almost simultaneously, in liquefying the majority of the so-called permanent gases. Their success was due to a recognition of the fact that reduction of temperature was necessary as well as pressure, but it was not possible by the aid of the methods and appliances which they employed to obtain the liquids in large quantities and to determine their physical constants. This was accomplished by Wroblewski, a chemist in Cracow, and he had Olszewski first obtain quantities of oxygen and nitrogen in the liquid state and describe many of their properties. These two investigators share with Dewar, an English chemist, the honor of having first devised practical methods for the production of liquid air in quantity. And in 1896, C. Linde in Germany and W. Hampson in England constructed technically efficient forms of apparatus for producing liquid air. Liquid air has not as yet, however, found any technical application upon a large scale. Nearly pure oxygen is obtained from it very cheaply, and the attempt has been made to apply it in the manufacture of explosives, but so far liquid air has achieved the most important results in chemical research. In the first place, it must be mentioned that Dewar, by its aid, has succeeded in liquefying hydrogen and in obtaining air, oxygen and hydrogen in the solid state, and that in doing so he has achieved almost everything that can be done in this direction. However, he is at present attempting to reach the so-called absolute zero. The results that have been obtained by means of this agency with respect to the discovery of the noble gases are of greater importance. Since these have been described, it only remains to be stated that Owens, in his cryogenic laboratory in Leyden, has recently announced that he has liquefied helium and that it boils at negative 268.5 degrees Celsius. End of section 18.